Okay, so we've been talking a lot about how the various derivatives, I want to add something to the directions, how the various derivatives tell us about the shape of a graph. What we're going to do now is we're going to start putting it together to actually create the graph of a function. Now, you're going to have some problems like this at the end of section 4.3, which we're finishing up now, and then section 4.5 is all about graphing. Okay. I'm just going to caution you, read the directions to see what you're asked for. Okay. So for some graphs you might be asked for all sorts of things, and for other things just some stuff. Okay. So here I'm asking us to graph this function said to include all intercepts, so that would be the x and the y intercept, maxes and mins, and points of inflection. Okay. And I didn't bother to write it out, I'm just going to vocally say it. We're going to want to make sure that our graph is increasing and decreasing on the appropriate intervals, and that it's concave up and concave down on the appropriate intervals as well. Okay. So we're going to get some information from f, we're going to get some information from f prime, and we're going to get some information from f double prime. Okay. I'm going to, as I get the information, I'm going to graph it over here. Here's my x and y axis. So let's start with what we can get from f. I can get the intercepts there. So if I wanted to find the y-intercept, remember that's where the graph is going to cross the y-axis. So that's going to be where x is 0. Okay. So it's going to be x is 0, and then I've just got to plug it in. So I'll look at what f of 0 is, and that's going to be 0 minus 0 is 0. So it turns out the y-intercept is just the origin. Okay. If I want to find the x-intercept, or septs, I've already found one of them because the origin is on both the x and the y-axis, but it's possible for a graph to cross the x-axis more than once. And if we're on the x-axis, that means our y value is 0. Okay. So I'm going to set y equal to 0 and solve for x. So x cubed minus x squared equals 0. I can factor out an x squared. So either x squared is 0, or x minus 1 is 0, x is 0, or x is 1. So the intercepts would be 1, 0, and 0, 0. Do make sure your intercepts are points. They're not just numbers. 1 isn't an x-intercept. 1 is an x value of an x-intercept. The intercept is actually the point. Okay. So I'm going to add that point to my graph. Excellent. These are the places where we can cross the axis. Okay. Now, with some functions, there might be other things like asymptotes that we're looking for. This happens to be a polynomial, and polynomials are never going to have asymptotes. So, I'm going to move on to the information that I can get from f prime. So, f prime of x would equal 3x squared minus 2x. Notice that that's always defined. Okay. So, let's see where it's 0. 3x squared minus 2x equals 0. You can factor out an x times a 3x minus 2. So either x is 0 or 3x minus 2 is 0. This would mean that x is equal to 2/3. So these are my two critical numbers. I'm going to draw them. I actually want to be able to keep my number line. So I'm just going to erase the problem and draw it up here. So this is my number line for f prime. I'm marking off 0 and 2/3. For a number smaller than 0, I'm going to try negative 1. So looking at the factored form, this is the derivative in factored form, I'm going to get negative. This would also be negative, because this would become negative 5. A negative times a negative is positive. Between 0 and 2/3, I think I'll just plug in 1/3. So x would be positive. 3 times a third would be 1 minus 2 is negative. Positive times negative is negative. And then bigger than 2/3, let's just plug in 1. So 1 times 3 minus 2, that's positive. So we're going to go up, we're going to go down, we're going to go up. Which tells me from the shape of the graph, I'm going to have a max here and a min here. Now, at 0, I already know what the y value is. it's 0. I know how high up that maximum is. All I'm going to do over here is just sort of draw in a little mountaintop. So when I play connect the dots later on, I remember that that's supposed to be a high point. For 2/3, I know that's supposed to be a minimum value. Sorry, this isn't 2/3, that's 1. Should have labeled that. So at 2/3, there's supposed to be a minimum value. I want to know how low down to go. So let's take a look. F of 2/3, my function, remember, was x cubed minus x squared, I think. Yes. Okay. So 2/3 cubed minus 2/3 squared. So let's see, that's going to be 8/27 minus 4/9, which is 8/27 minus, let's see, times 3/3 is going to give me minus 12/27. So negative 4/27. So there's going to be some point here. This was 1, this is about 2/3. I'm just going to guesstimate that's about where I want to come down to. I'm going to indicate that that's a minimum value, and I'm going to label it as 2/3 negative 4/7. Okay. So, super important when you're finding maxes and mins, they're points on the graph. Make sure you find both the x and the y value. Okay. Excellent. So now I want to try to find the points of inflection, and in doing that I'll find the intervals where things are concave up and concave down. Okay, so if this was f prime, f double prime of x is just 6x minus 2. That's also always defined. 6x minus 2 equals 0 would be when 6x equals 2. So x would equal 2/6 or 1/3. So for my second derivative, and I'm going to just line that up here with the first derivative. I think I can erase the calculations as long as I remember that we're looking at 6x minus 2 is what we're plugging into. Okay, so we had just one critical point, or not critical point, one possible point of inflection, which was at 1/3. If I pick a number to the left of that, I think I'll pick 0. That's going to give me something that's negative. If I pick something to the right of that, I'm going to pick 1 just because it's easy to plug in, and that's going to give me 6 minus 2, which is 4, which is positive. But you'll notice this interval here to the right of 1/3 includes the location of my min. So I'm really glad that we got that this was concave up, because concave up shapes do have a min. So there's sort of, if I line things up, there's a built-in check. If I had somehow gotten that this was a max and then I got concave down, I'd know I had done something wrong, so I'd want to go back and find that. Okay. All right, so that tells me that I have a point of inflection. A point of inflection is a point. At this point, all I know is the y value. But f of 1/3, the original function, would just be 1/3 cubed minus 1/3 squared. So that's 1/27 minus a 9th. That's going to be 1/27 minus 3/27. That's going to be negative 2/27. So I want to plot that. Okay. So that's going to be right in between this max and this min. It's at 1/3. Here's 0 and 2/3. Here's 1/3. And we're down at negative 2/7 when this was down at negative 4/7. So now we're ready to play connect the dots. And we have 1, 2, 3, 4 dots, but we have a whole lot of information. Because I know that as I connect them, I've got to go up, down, up. And I've got to be concave down until I hit my point of inflection, at which point I'll switch. So I'm going to come up, being nicely concave down, pass through the max. When I hit that point of inflection, I'm going to switch from being more of an umbrella shape to more of a cup shape, pass through the min, keep coming up. And now it's really easy at this point to say, oh, I'm almost done, hooray. And did you see what I did? I just changed the concavity. Oh my goodness, we don't want to change the concavity. We've got to continue going up and being concave up. So after I've connected the dots, I always like to just look back at my number lines and say, did I go up, down, up? Yes. Was I concave down and then concave up? Yes. And sometimes, especially if you're sort of guesstimating things on the scale, sometimes you sort of have to adjust the points, because if you're not drawing things exactly to scale, you might put a point in such a way that, oh, I'm supposed to hit this point, but I can't do that without changing concavity. So you need to adjust and be close enough to the right scale that you can respect the increasing and decreasing in the concave up and concave down intervals. Okay. All right. This is the only example of this I'm going to do in section 4.2. There are a number of questions that do ask you to just graph things, but that's really what 4.5 is all about. So we will be doing plenty more examples of this when we get to 4.5. So I would encourage you to, with 4.2, do all of the homework that doesn't involve just graphing things. Start on the graphing things, but if you get stuck on that and you feel a little bit behind, go ahead and watch the videos for 4.5 and then return to those graphing questions once we've talked a little bit more about them.